Hi, my name is Jordan Ford. This is the 15th time we made this video. Try it again. Okay. Today I'm going to be talking about fully differential filter design, how to design a fully differential filter using fully differential op-amps, and how to take a single-ended design and turn it into a differential design. So the first thing we're going to start with is a second-order single-ended filter using multiple feedback topology, which hopefully you guys have seen before. Okay, so this is a second-order filter. It has a transfer function that looks like this. Okay, so K is your DC gain. Omega naught is your corner frequency in radians for a second. Okay, let's label our resistors here. We got R1, R2, C1, C2, and R3. So in terms of your resistors and capacitors, K is negative R2 over R1. Q is R2, R3, C1, C2, that's 1/2, divided by C1 times R1 plus R3 plus K R3. And omega naught equals 2 pi F naught equals 1 over R2, R3, C1, C2, square root of. Cool. Hopefully you guys are familiar with multiple feedback topology. If not too hard. It's just a standard form for a filter. Okay, let's turn this into a differential filter. So, I'm going to move down here. So basically what we're going to do, it's a little bit convenient because we're using fully differential op-amps, but we're basically going to duplicate our circuit on both sides of the op-amp. Let me draw this a little bigger. Okay, so intuitively this should make sense. It's really just that duplicated and flipped over. Here we have Bn minus, Bn plus. For those of you that haven't been exposed to a differential signal before, you'll see them a lot in things like a high-speed serial interface. But basically it's two wires where the value on the wire is always opposite of the other wire. So if Vn plus is a 1, Vn minus is a 0, and vice versa. One of the most important figures of merit for a differential filter or a differential circuit is common mode rejection. So basically if some physical process biases both wires up by a DC amount, then shouldn't really affect your output because your output depends only on the difference between the two. Okay, so, and we'll label this in a similar way. So this is R1, R2, R3, C1, C2, C1. This is going to be V out plus V out minus. Okay. Cool. So now we've got our filter topology. Let's pick some resistor and capacitor values that give us, let's work through an example of an actual filter design. So I'm going to erase this singleted version. Hopefully everybody got it written down. But our task now is to determine real values for R1, R2, R3, C1, and C2. So first we need to define what we're trying to build here. So let's build a second order filter. Fully differential, obviously. Let's choose F naught equal 1 megahertz, and let's make it low pass. So our filter is going to look something like this, where this is 1 megahertz. Right, low pass filter passes low frequencies, attenuates high frequencies. So I'm going to walk you through component selection. The first thing we need to do is figure out where we want the poles of our filter to be. This should be a similar idea to a single-ended filter design. Let's say for the sake of example, let's choose the following transfer function. So h of s equals -1 over -0.79575 s squared minus 1.4705 times 10 to the -10 s minus 1 over 1.8. Okay. Oh, this is times 10 to the -7. Cool. I'm going to move that out of the way. Alright, so this comes from the normalized Butterworth polynomial for a second order filter. Basically, you take the normalized filter and you plug in your 1 megahertz corner frequency. So let's take this and find some resistor and capacitor values. So an approach that I like to use for determining resistor and capacitor values is, in this case, we can say that R2 and R3 are integer multiples of each other. So R2 times some factor m equals R3, and C1 times some factor n equals C2. And now we've reduced it kind of more to a problem of 2 variables instead of 4. So we'll pick R2, well, we'll pick a C1 and a C2 and get an n. So let's pick C1 equals 100 picofarads. It's kind of just a convenient value. And let's pick C2 equal 470 picofarads. And let's see if that gives us a reasonable value for n, or, well, a reasonable value for m, and then reasonable resistor values. So, okay, so this equates to an n equal to 4.7. All right. So Q, based on this, we can work out that Q equals 0.5412, which equals the square root of 2mn over 1 plus m times 1 plus k. All right, and we know that k equals 1.8, so k equals 1.8. We already chose m equal 4.7. So we can solve this for m. We get m equals 3.34. Cool. So given our m, we need to work out r and, well, we've already got c's. So we need to work out what R2 is going to be. So we know that omega naught equals 2 pi times 1 megahertz, so times 10 to the 6th. And that's also equal to 1 over R C root 2mn. So where this is C1, this is R2. Okay, so now we plug in m is 3.34, n is 4.7, C1 is 100 picofarads, solve for R2, we get R2 equals 284. And from that, we know from the DC gain of 1.8, we can find that R1 will be 157.78. And because R3 is m times R2, we get R3 equals 948.8 ohms. Cool. So now we've got real values for all of our resistors and capacitors. One problem we'll face is when choosing actual values for these, you won't find a 948.8 ohm resistor on DigiKey or wherever. So you're going to have to round to the nearest standard 1% value. So instead of 284 ohms, we're going to use 287 ohms, which is about a 1% error. Instead of 948 ohms, we're going to use 953 ohms, which is 0.4% error. And instead of 157.78, we're going to use 158, which is a 0.14% error. All of those I can live with. And then C1 we already picked was 100 picofarads. And C2 470 picofarads. And we've successfully designed a fully differential second order low pass filter using Butterworth coefficients. It has very good common mode rejection because it uses a fully differential op amp. I have a part number here. We could use one example. Since we spec'd out all our resistors and capacitors, we might as well spec out our op amp. So this could, one op amp you could use is the THS 4141 from TI. And that will give you an excellent filter. Thanks.